Hey, good morning, everyone. Today we're going to talk about level 1 visibility. Now, as nice as it would be to have the budget and the time to deploy network sensors at every single level in the network, that's just not worth it. And Dale has touched on this in some of his articles, and you as the S4 attendees also seem to understand this. So I put out a poll before this talk to understand how much trouble it would be for you, the S4 community, to deploy network visibility down at the PLC level. And about 40% of you described it as a significant challenge, 25% said difficult, and 10% said completely overwhelming. And so why is that so difficult? You have to do major hardware and architecture changes, deploying all those managed switches if you have really old switches. You have to deploy all those network sensors. That takes a lot of labor and a lot of hardware costs. For all that effort, you don't really get any idea about what's going on inside the PLC. You're only seeing what's happening on the network, and PLCs, to be honest, don't really talk that much unless someone actively logs into them. You don't really see anything useful about the internal health of the PLC. So you go through all that effort, you go through all that cost, and you really get little you get some return on security, some return on maintenance value, but you really don't get that much. So what I'm arguing today is that level 1 endpoint visibility is a much more effective approach because it's just using native ladder logic agents inside of the PLCs, and it's providing deep insight valuable to both the security side of things as well as the everyday controls engineers on the OT side. So a little bit of background before I get into the PLC-specific stuff. So this is kind of translating EDR, endpoint detection and response, for IT, translating it into the PLC world. So the original definition of EDR for IT was coined back in 2013 on the Gartner blog. It's originally defined by 4 key capabilities for endpoint-specific data: collecting the information about a system, centralizing it somewhere, some central location, being able to explore that data for forensics and investigation, and then doing analysis to automatically be alerting on interesting events happening. So how does that look when we translate it into the PLC world? You can kind of call it Controller Endpoint Detection Response, or CEDR for short. So level 1, we're talking about the PLCs, the RTACs, the RTUs, and DCS controllers, basically anything with some level of basic programmable functionality. And when we look at the collect step, there are a bunch of IT-related metrics and data that we can collect. So it's kind of standard IT stuff, but there's also a lot of really cool and useful information native to the PLC that we can collect. So the scan cycle time, how long the logic is taking to execute, all those different fault messages and fault information. So those are things we're collecting for PLCs. Step number 2 is to centralize. So this can be using the native ICS protocols, or you can be a little creative and create your own lightweight collection techniques that we're going to talk about later. Step number 3, explore. The theme of this conference, in this case, is just referring to being able to explore all that data in a historical investigation. And finally, analyze. The focus, most of what we're talking about today is all the kinds of interesting detections we can do with all that information coming from the PLCs. So first step on the collect side, we can get a lot of good things from the top 20 secure PLC coding practices. So if you're not aware of that, there's just good practices out there to help program PLCs more securely. And they have a lot of good monitoring suggestions that we can use to build up our PLC EDR. So watching the operating mode, whether it's in run or program mode, it's a very obvious good detection. Operators and security people should be alerted and make sure they know, is this PLC in remote program mode, or is it in run mode, the suggested way you should be doing things. Watching the system uptime. Has the PLC rebooted unexpectedly recently? It's a very obvious, useful thing to know. Any hard stops or faults, also very useful to know, both from a security perspective. Faults could be caused by some kind of malformed packets being sent to the PLC, or it could just be bad programming, and the OT side would need to know that as well. Being able to watch the memory usage, other math errors and faults are also very useful. And then checksums, if the PLC has the program checksums, also a very obvious good detection. My personal favorite, what we're going to talk about a good bit of this talk, is using the scan cycle time. So scan cycle time is how long the logic takes to execute on these PLCs. And why this is my favorite metric to use for PLC kind of EDR is, first of all, it is ubiquitous. Every single PLC I've ever come across, the vendor provides some method for measuring the scan cycle time, because the PLC programmers need that information to actually make sure their code executes in time to perform whatever critical functionality it is performing. So that metric is available on every PLC. And it's nice that it's also replay resistant. It's not impossible to replay as an attacker, but comparing it to all the other metrics, it takes more work for the attacker. So all these other metrics are pretty static. The checksum value for the PLC program, that stays the same. Memory usage stays the same. Operating mode stays the same. So those are very easy for an attacker to spoof, some static value. But the scan cycle time, it's a continuously varying kind of like analog measurement, basically. Lots of samples, lots of variability in the behavior, and inherently it's harder for an attacker to accurately spoof. And so that's a nice advantage of using scan cycle time for these kinds of detections. So going beyond the top 20 secure practices, some other things that I found really useful, and we're going to talk about, is active forces. So some vendors on their PLCs, it lets you actually monitor, are there any currently active forces in the program? So that's useful for debugging purposes. Engineers will sometimes try to debug what's wrong with the control logic. They'll force a bit on, they'll force some variables just to try to work through the different parts of the program. And that is really useful to know that there are active forces and the program is not just running in normal mode. It's also a very easy way for an attacker to mess with things. If they are able to log into the PLC, they don't need fancy exploit knowledge. They can just force a bit on the program to potentially violate some safety check. Asset information. So most ICS networks out there are still struggling to actually get accurate asset information about everything on the network. You can actually get this from within inside the PLC for most vendors, being able to read the model, firmware, serial, and name of the PLC. You could read that and continuously stream it out over the network, comparing that to the network monitoring approach where you have to sit around and wait for that PLC to advertise or wait for someone to log into the PLC to get that information. So you get very rare samples. If you're passive monitoring on the network, you get continuous up-to-date samples of what that PLC is doing, what it is, using the logic on the PLC itself. And the really cool thing here is that on the network, if you're just on the network side, you would only be limited to seeing what's IP-based on the network, which you can stick a tap on or a mirror port on. Depending on the PLCs and the vendors and how it's set up, a lot of times you can actually also read the downstream serial devices as well to get their asset information, to see what all is connected to that PLC. You get a much more complete, bigger picture of everything inside of your control network performing control functions. Next thing is communication statistics. So this is really cool that without any kind of network sensor, some PLCs actually let you read statistics about their Ethernet communication and their serial communication. So I'm talking about like bytes transmit and received, bit errors, protocol errors. You can see that stuff in some PLCs without having to deploy network hardware. And again, depending on the exact vendor and PLC and setup, sometimes you can also even sample the downstream serial devices as well to get that information. So getting a much more clear picture compared to the network monitoring side. The centralized step, the obvious approach would be using polling using existing ICS protocols. You're already familiar with those. So the advantages here is standardized. The firewall port may already be open. The downsides here are that we all know these protocols are not secure. And if we are now relying on this data for security purposes to do security detections and security asset inventory, it would be nice. It would actually be really nice if we could encrypt it and authenticate it, but that's not the case for most of the ICS protocols in use today. Another disadvantage is inherently if you are relying on these protocols, that means there's going to be more things polling the PLC, more things interacting with the PLC over the network, which potentially opens up more attack paths for an attacker to get to the PLC, abuse that same path on the network to probe the PLC and potentially DOS it or brick it. Depending on your network, you may require some architecture changes to get all that data into a central location. And it's not ideal that you're starting to mix a bunch of process and security data. That security data may be overwhelming and confusing for the process engineers, and then vice versa. The other side of things could also be confusing to the other side. So it's not ideal that it's all being mixed together in the same protocol and the same PLC. My preferred approach is pushing with a custom one-way protocol. So most PLCs out there actually open up kind of like a raw TCP socket interface that you can write your own custom protocols, and controls engineers sometimes do that, write their own little custom protocols to send data through the network. And so you can do that here too, to start pushing out the PLC data using true unidirectional protocols. So you can actually use a true data diode if you want to be super secure, use UDP for the protocol. You don't need anything coming back into the PLC, so inherently it is a more secure way of getting data from the PLC out of the ICS network. So again, you can use that data diode if you want to be super secure. You can also just write much more strict firewall rules, only allowing certain outbound connections. And so it's a more secure approach. It's more flexible in that since it is your own custom protocol that you're putting on the PLC, it's a lot easier to piggyback on any open outbound ports. If you already have a really heavily locked down network, you could potentially piggyback on that existing open port. And we have actually tested implementations written in pure native structured text for some lightweight stream ciphers. So you can actually provide your own application layer encryption for streaming this data out of the PLC. The disadvantage here is that the PLC agent code does become more complex, and depending on how old and how bare bones and fragile the PLC is, it may not be able to handle the stream cipher, or it may not be able to handle some of the more bigger detections that you can do from the PLC. The explore step is pretty self-explanatory, just being able to explore all that data. And this screenshot here, we're looking at scan cycle time, free memory, and the network bytes received. So this is looking at some unlabeled event. We're actually going to analyze this event in the next few slides. So we'll move on to the next one. For the analyze slide, first of all, starting with the more obvious, simple things. You can do per metric event detections for all the obvious things you want to detect. When does the audit value change? When does the program checksum change? If the PLC has it, it's a very obvious, good detection to have. Did the PLC reboot? That's a very obvious, good detection to have. Free memory starts to get a little more complicated. Depending on the PLC, it's usually very static, and so it's usually a good detection to have in place. Does that free memory change at all? Getting a little more complex now, if you're able to monitor the bandwidth, the network stats on the PLC, you can start to do some basic network anomaly detection just purely within the PLC, or with the PLC agent. So being able to detect network scans, port scans, and potentially network DOS attacks just from watching that bandwidth behavior. And again, my personal favorite, scan cycle time. You can do some really cool detections on watching, building up a profile of what the scan cycle behavior normally is for that PLC, and being able to detect when that behavior changes, which could indicate a PLC program change, some kind of malware infection, some kind of other ongoing denial of service attack that is burdening a CPU and slowing things down. Going one step further, you can start to aggregate and correlate all those somewhat meaningful, somewhat meaningless events together into a more meaningful story. So if you see a bandwidth increase followed by a memory decrease followed by a scan cycle behavior change, you can combine those three kind of simple events into a larger story of this looks like a user logged in and made an online change to the PLC program. So we're going to walk through how we do this in this example here. So again, we're looking at scan cycle time, free memory, and the network bytes received. And we can look at the normal behavior here for the scan cycle time on the top. You see just with the human eye, you can kind of see two major states. It's kind of alternating between kind of high and low, slow and fast cycles. And then we see, if you look closely enough, there's two other minor states in that scan cycle time behavior. So it's pretty stateful metric. And we can use some stateful machine learning to find those states and then alert when we see any behavior that deviates from those known states. The next one, free memory in the middle, is pretty static on this PLC. It does not change at all under normal circumstances, and so it's a very easy detection for alerting on an increase or decrease. Finally, at the bottom there, we have the network statistics, the network bytes in. It's a little noisy, but looking at the average, it stays pretty in bounds within that average. We can use a basic like mean and standard deviation, very simple statistical test to see if there's any anomalies there. So that was all normal behavior. Now we're looking at some unlabeled unknown event. This PLC started acting weird. We had this historical capture of all this raw data, the scan cycle time, free memory, and network bytes in. So doing the easiest, obvious one first, looking at that free memory, we see 4 memory decreases pretty back-to-back, and then a memory increase. So on its own, there's not much context there, but it is weird, it is interesting. The memory changed on this PLC, and we had those timestamps of exactly when and how much it changed. The next one, getting a little more complicated, just using that basic mean and standard deviation detection. Looking at the network stats, we see a giant, very short spike at the very beginning, and then we see kind of a sustained lower anomaly at the end. So anything highlighted in red is a identified anomaly, and we see the behavior there was a giant spike, we identified in red as an anomaly, and then kind of sustained lower anomaly after that for a minute or two. So again, by itself is somewhat interesting, but we don't have much context. We can't really start to build a story around what's happening there. Now getting to the scan cycle time, before we get into those detections, we have to provide a little bit of background on how scan cycle times work. And specifically, we're looking at Rockwell, because this was done on a Rockwell PLC. We're talking about task priorities first. So you can have different tasks on the PLC doing different things, and higher priority tasks will always interrupt lower priority ones. So you have safety critical tasks, those are going to be the high priority ones. They're always going to interrupt any low priority ones. The highest is level 1, the lowest is level 15, and there's some specific levels for different tasks, like the motion planer is always the highest priority. The I/O task is always priority 6, and the continuous task, the most interesting one for us, is always the lowest priority above level 15. So the continuous task, like I said, is always the lowest priority, and it is executing as fast as possible, not waiting around for anything else to happen. So essentially, it is using up all the free CPU cycles on the PLC, and it can kind of be a stand-in for basically how idle or how busy the PLC was. It is too much work to log every single scan cycle when you're talking about microsecond or millisecond scan cycle times. So you can kind of build an average of these scan cycles by just counting how many scan cycles have been executed, sampling that count once a second, and you can average that to get like an average per 1 second. Some other background on these kinds of detections. We are using some clustering algorithms. In general, that's just ways to group data together into similar clusters. Usually, most clustering algorithms require you to know how many clusters to look for before you even run them. But for the mean shift clusterings, what we use in these experiments, you don't need to know the exact number of clusters. You just kind of like an upper bound of starting with an evenly spaced number of centers as guesses, some upper bound of the number of clusters. It iteratively shifts towards their local mean, and you finalize by merging the overlapping centers. So that little animated GIF there kind of illustrates how that works. So you start with evenly spaced centers. They just iteratively get closer to their local mean. And then eventually, when they stop moving around those iterations, you've converged and you can overlap, you can merge all those overlapping centers to find these 4 clusters. And then identify anything coming in. Does it belong to one of these clusters? How far away it is from one of these clusters? If it's very far from any known state or any known cluster, then it's an anomaly. Then finally, kind of the last piece of this is we found using basic error thresholds, it's not very effective. It's pretty noisy because it doesn't consider any of the recent history and what's been going on. And so a very simple approach, this is actually taken from old process control methods, the QSUM, cumulative sum method. The basic idea here is that you're accumulating error from how far the observed value is from what the expected value is. And so we can use this with our stateful detection to do some basic kind of accumulating error of how far off the behavior is from what we've seen. So super high-level pseudocode here. Just every sample that comes in, you find the closest known state from the closest known state. Then you calculate the distance for that closest known state, and then you feed that into the QSUM detection for thresholds. So finally, looking at this scan cycle time event detection, the main interesting graph up there is the one at the top. So that's what the scan cycle time was doing, and then our detections. We show you here the absolute error and the QSUM error just to kind of illustrate what's going on behind the scenes and how obvious the attacks are. If you look closely up there, we see that the first little blob of red happens after this little spike in the bottom of the scan cycle time. We see another spike, and then we see a consistent change in behavior for all that scan cycle time. And so this is all based on those 4 horizontal black lines you see. Those were the 4 states that we found using the mean shift algorithm, and then the detection thresholds were determined using the QSUM method, and that's how we are wording here. So we're finding some changes in the scan cycle time behavior that could indicate some changes in the logic or something burdening the PLC, something slowing down the scan cycle time to cause these deviations. So now putting all that together, it starts to make a little more sense. We can actually make more sense of what was going on here. We see a lot of the events are lining up at the same time, and we can use our experience with PLC events and what these are normally doing to start building up a more meaningful story. So we see around time equals 29 seconds, we saw a network anomaly at the same time as a scan time anomaly. And so based in our experience, really the main things that cause that are either a hard network scan or a potential DOS attack. So a huge spike in bandwidth and something slowing down the PLC that's most likely a port scan or some kind of DOS attack. Next one, we saw a network anomaly at the same time as a scan time anomaly. At the same time as a memory decrease. So just based on our experience watching all these events on the network, we can combine all those together to say that when we see all those kind of in the same time period, that is a user login event. If the bandwidth increases, we see memory decrease, and we see some effects on the scan cycle time, that really usually only happens when someone logs into the PLC. So now we've detected someone's logged into the PLC, followed by the memory decreasing 3 times, consecutive times. We can use that knowledge to say that when the memory decreases 3 times after a user has logged in, that pretty much only happens if the user is making some online changes, online edits to the PLC program. Finally, we see the memory increase again and the network anomaly ends. Again, based on what we're seeing in PLC behavior, we can identify that pretty accurately as that really only happens when someone logs out of the PLC. When a network anomaly ends and the memory increases again, when someone logs out, it frees up some memory on the PLC, it stops the bandwidth coming into the PLC, we can identify that as a user log out event. So now we have this whole complete story, which is exactly what actually I did to generate all that data. I first did a hard nmap scan, which we identified there. I logged into the PLC. I made 3 separate online edits, which we were able to identify through these detection techniques, and then I logged back out. So we had this full, complete story of network-related events, all using native ladder logic information coming from the PLC. So in conclusion, controller endpoint detection and response, or CEDR, I'm arguing is a much more effective approach to getting visibility down at that level 1, because you don't have to go and deploy a ton of network sensors. You don't have to go configure a bunch of mirror ports. It's just native ladder logic. And it's giving a lot more deeper insight than what you could get just from the network. You can't see scan cycle time from the network. You can't see memory usage. You can't see a lot of this stuff just from the network. But you see it from inside the PLC. And you can do some pretty interesting detections using all that data. And then aggregate all that into a more meaningful story. So with that, I'd like to thank you for your time. If you have any questions, please come up to one of the mics on either side of the room, and I'll be happy to answer.
In your experience, what's the impact on a PLC if I implement my custom protocol to push out the data?
Yes, so what's the impact of adding a custom protocol to push out the data? It does take more to do that, like I said. So using the native ICS protocols is lighter weight and easier. In our experience, the protocol itself is lightweight. It's honestly lighter weight than all the other ICS protocols. So it takes up, we've measured like less than 1% scan cycle time overhead and CPU overhead. And as far as memory, the memory overhead is a little more depending on how you write the protocol. So I think it's like a few hundred bytes or a kilobyte of memory to implement the custom protocol. But in general, it is definitely acceptable. It's very low, lightweight overhead. It's a great question, though. Thank you.
do apologize if I missed this in the early part of the meeting or the presentation, but when you mean by creating detection using the data, you mean just like writing up like a Suricata rule and just throwing it in some type of EDR system?
So when I'm talking about detections here, we're kind of using our own custom detections to do the ML, the data analytics and machine learning. So we aren't using any of the custom, like we aren't using Suricata rules or anything like that. The PLC is pushing out the data to our EDR server, kind of general EDR server, and we're doing the data analytics and machine learning to generate those events. Yeah, great question, thank you.
How's it going? Thank you for your talk. I walked in a little late as well, so I apologize if you already covered this. How far back have you tested this with more legacy PLCs, going back 10, 20 years? Would you expect and see the same results as you would from something that was put out maybe 5 years ago?
Yeah, so comparing older legacy PLCs with newer PLCs, so there's pros and cons. So newer PLCs usually have even more interesting things that we can read off and do some more interesting detections. The legacy PLCs don't, and they may not have as much memory to implement like the custom protocol approach. But focusing on the scan cycle time detections, because the older PLCs are so much lower powered and more bare bones, the scan cycle time detections are even more obvious. They're even easier when you go back and look at the older PLCs. So it's a trade-off. So the scan cycle time detections become even more accurate the further back you go, but you may not be able to read like the memory usage or the program checksum probably doesn't exist on a lot of those older PLCs.
Understood, thank you.
Thank you. All right, I don't think I see any other questions. So thanks again for your time.